Okay. Hey, we're back. This is AP Physics 1. I'm going to do it with the screencastify to get a sense of how to answer this free response problem, experimental design with springs. So you have this set up. Spring can be assumed to be ideal hands from a stand as the one in the figure below uh, or above. You want to be able to determine experimentally spring constant K of the spring, assuming you have all the equipment found in a normal physics lab. What commonly available equipment would you need? Okay. I think if I write with this, I'm assuming there are different ways you could go about doing this. Probably meter stick and mass hanging from it, or a force sensor would be one way to go about doing it. Another way to do it would be with a stopwatch and a mass. So there are two different ways that I think you probably could go about doing this experiment. So we're going to talk about both just so you understand it, because this was an actual AP Physics B back in the day problem, and they allowed for two different ways to do it. And so one way would be to possibly hang a mass from the spring, and then you could measure different things from it. So if it stretched a certain amount, you'd measure that, and you knew how much it weighed. So that would be one way. We did that in the lab. That's probably the way I would expect most people to do it. When I said a force sensor, you could also lay this horizontally and pull the mass with a certain amount of, the spring, pull it with a certain amount of force, and then it would elongate the spring. You could measure it. So either way would work. And the other would be using that spring, hanging the mass, and let it oscillate in simple harmonic motion. And in that case, you could measure the period of oscillation, and from that, maybe get what the spring constant was. So those are the two different ways you would think about doing it. And how would you determine it? I'm thinking that you would say your force due to gravity is equal to the force due to the spring. And so you go mg equals k, maybe delta x, and your k would then just be equal to mg over delta x. Or if the case of the force sensor, it would be the force over delta, the length. The other way would be using the equation for simple harmonic motion, 2 pi square root m over k, and you could measure the period and thereby calculating what the k was. You obviously have to square both sides and that kind of thing. But those would be the two different ways you could go about doing it. And the committee, when they graded it that year, either way was sufficient. So then they say, well, how about if you just go ahead and show that we can do this calculation? So remember that the 2 pi square root m over k equation is going to help us, but that's equal to the reciprocal of the frequency. So the frequency is going to be equal to 1 over 2 pi square root k over m. And so let's plug in some numbers and see what we get. We've got 500 newtons per meter, and we're going to divide by 2 kilograms. And so that particular year, they were a little bit worried about, or they wanted to make sure that you showed that you understood units. So that was part of it. And so when you do that, if you take a look at Newton as a kilogram meter per second squared, the kilograms are going to go away, the meters are going to go away, and you're going to get square root of, let's get back to, this ends up being 2.5, and it's 1 over second squared. When you take the square root, you get 1 over seconds, which are hertz. So the answer to that is 2.5 hertz. So that's the answer to part B. The next one says, suppose you have a spring that has a maximum value of 25 newtons. I think your problem said 20. I just changed it to 25. It was supposed to be 25. But you want to use that spring scale to measure something that weighs more than 25 newtons. How would you go about doing it? Draw a clear diagram that shows. And again, there are different ways that you could go about doing that. And I'm going to tell you the one that I would expect would get it done pretty easily is if you use that as a lever. And so I've got a fulcrum here, and I've got this mass over here, and I have the spring scale over there. And so you'd kind of look at the fact that there would be different distances away. If you remember from that, if M is going to be bigger than that force, then maybe X1 is less than X2. But this would go that some of the torques on either side are going to balance each other out. So you'd basically have the force on the spring scale times X2 is going to equal the weight of that object times X1. And so the weight of the object is just the force on the spring scale times X2 over X1. Pretty straightforward thing. And they would want you to be able to show that you did that pretty quickly. Other things you could use for that they wrote down is you could use an inclined plane or a pulley system to figure that out. But you'd have to show how it worked. And they said, as long as you don't violate things or say that you're using a frictionless inclined plane, which doesn't seem that realistic, you're probably not going to get full credit. But knowing that just weighing things on two sides isn't going to get it done, your spring scale, you're going to have to do something with a mechanical advantage, i.e. using some sort of an lever or a pulley or an inclined plane. So you're using some sort of a simple machine to get the job done. Okay. So basically that's the answers that I was expecting for that one. Hopefully that approach to solving problems where you can watch me do it makes sense. If you have any questions, give me an email. Otherwise, we'll talk to you next time. Thanks a lot. Stay safe.